Our next chapter is on the dynamic performance and the performance limits of a vehicle. And we start this chapter by looking at coupled tire models. Recall that the purpose of tire models is to provide a mathematical formula for the forces and moments acting on a tire in its contact patch. So in particular, the longitudinal tire force acting in the longitudinal direction of the tire, the lateral tire force acting in the lateral direction of the tire, and the vertical tire force acting vertically on the tire. Then also the aligning torque mz, the overturning moment mx, and the rolling resistance moment my, even though these are of minor importance and the last two are not considered at all in this course. So far in this course, we have predominantly looked at lateral tire models, which couple the lateral and vertical tire force with the slip angle alpha of the tire, and at longitudinal tire models, which couple the longitudinal and vertical tire forces with the slip ratio of the tire. However, as you may have guessed before, in practice, the lateral and longitudinal tire models are not really independent of each other. In particular, the maximum combined force, which is defined as the geometric addition of the lateral and the longitudinal tire forces, is limited by the friction circle of the tire road contact. And this friction circle is of course defined by the tire road friction coefficient mu. What this means can be illustrated graphically in a planar diagram whose axes are the longitudinal tire force and the lateral tire force. The friction circle, shown in green here, is a circle centered at the origin of this diagram with radius mu times the vertical tire force, where mu is the tire road friction coefficient. Now, the combined force of the longitudinal and lateral tire force may not exceed the friction limit, meaning that the force has to be inside the friction circle. This is, for instance, the reason why you should not brake in a curve when you're driving at the performance limits of a car. Instead, when you're driving a car at the limits of its performance, like for instance on a racetrack, the driver has to brake before entering the curve, because otherwise, if he's braking and steering at the same time, the combined tire force easily exceeds the limits set by the friction circle. Moreover, even below the friction limits, an increase in the magnitude of the slip angle decreases the magnitude of the longitudinal tire force. All other factors, of course, being equal, in particular the slip ratio sigma x. Similarly, an increase in the magnitude of the longitudinal tire slip sigma x decreases the magnitude of the lateral tire force. Again, all other factors, in particular the slip angle alpha, being equal. For an example, suppose the slip angle alpha is equal to 0, and for a fixed slip ratio, this is the longitudinal tire force that we get. What we do now is we gradually increase the tire slip angle alpha, and what we see is first, a lateral tire force builds up, and second, the longitudinal tire force is reduced by an increasing tire slip angle alpha. In fact, for a constant slip ratio sigma bar x and minus sigma bar x and a varying slip angle alpha, the longitudinal and lateral forces produced by the tire take the form of an ellipse in this planar diagram. If instead we pick a slip ratio that's smaller than sigma x bar and again vary the value of the slip angle alpha, we get another ellipse that is now more slim than the ellipse that we had before, and so on. Next, we will proceed to look at a few specific coupled tire models. The first model that we consider here is the derated Fiala tire model. In this model, the longitudinal tire force is given by the product of the longitudinal stiffness of the tire times the tire slip ratio if the longitudinal tire force does not exceed the friction limit, and if by this formula the longitudinal tire force would exceed the friction limit, then it is set to exactly that friction limit. If we illustrate this graphically in a diagram where fx is plotted over sigma x, we see that this is basically equal to a linear tire model which is saturated at the maximum available friction force mu Fc. The model for the lateral tire force is similar, except that its maximum is derated by a factor psi, which is defined by this expression. And the purpose is to keep the combined force inside the friction circle. So the lateral tire force is given by this expression, which can again be interpreted graphically by representing the lateral tire force Fy as a function of the slip angle alpha. And we see again that we have basically a linear tire model, which is now saturated at the friction limit times the derating factor. The second coupled tire model that we'll look at is the Pachitea-Sharp model. The main assumption of the Pachitea-Sharp model is that the longitudinal and lateral tire stiffnesses are the same. So C alpha equals C sigma, and we define the stiffness value as simply the letter C. In reality, however, the two stiffnesses are rarely the same. So this is really a simplifying assumption that one might be willing to make for the sake of the simplicity of the resulting model. Next, we define the lateral slip ratio in analogy to the longitudinal slip ratio as the longitudinal velocity of the wheel multiplied with the tangent of the slip angle alpha divided by the rotational speed of the wheel and the effective radius of the wheel. Using this, the combined tire slip sigma can be defined as the geometric addition of the longitudinal and lateral slip ratio, and the combined tire force F is given by this cubic expression as long as the friction limit has not been reached, and it's given by the friction limit as soon as the limit has been reached. The longitudinal and lateral tire forces are then given by their corresponding share of the combined tire slip. So for the longitudinal tire force, we need to take the fraction between the longitudinal tire slip and the combined tire slip times the combined tire force. And for the lateral tire force, we need to take the lateral tire slip divided by the combined tire slip times the combined tire force. The third and final coupled tire model we'll look at in this section is the Dugov tire model. The main advantage of Dugov's tire model as compared to the Pachitea-Sharp model that we have just seen is that the Dugov tire model allows for two distinct values for the longitudinal tire stiffness and the lateral tire stiffness. So we denote these two distinct values by C sigma for the longitudinal tire stiffness and C alpha for the lateral tire stiffness. For the Dugov model, there actually exists a full analytical derivation. However, here we only present the resulting model equations. The longitudinal and lateral tire forces in the Dugov model are given by these two expressions, where f of lambda in both expressions represents a scaling factor less than or equal to 1, that is calculated as we will see in just a moment. Moreover, the factor 1 over x that is present in both expressions is approximately equal to 1 as long as the slip ratio turns out to be much smaller than 1. And since the slip ratio usually is much smaller than 1, this can be seen as another correcting factor. If we neglect these two factors for the moment, what remains is a linear tire model in both cases. So for the longitudinal direction, Fx is equal to the longitudinal stiffness times the slip ratio. And for the lateral tire force, what remains is the lateral tire stiffness times the tangent of the slip angle alpha. In order to compute the scaling factor f of lambda, we first define the longitudinal tire force and the lateral tire force without the scaling factor, which we call f tilde x and f tilde y. Then we define a parameter lambda as mu fz, where mu is the tire road friction coefficient and fz is the vertical tire force, divided by 2 times the geometric sum of the unadjusted longitudinal and lateral tire forces. The scaling factor f of lambda in the interval between 0 and 1 is now defined as 2 minus lambda times lambda if lambda is in the interval between 0 and 1 otherwise. If we make a little sketch of that function f of lambda, this is what the function looks like. So in the interval of lambda between 0 and 1, the function has a parabolic shape, and for lambda above 1, the function is just constant and equal to 1. Finally, in order to get a better insight into the Dugov model and to better understand how the scaling with f of lambda works, let's consider two cases. First, suppose the unadjusted longitudinal and lateral tire forces are small, so the geometric sum is close to 0. Then, as a consequence of this expression, lambda will go to infinity, and hence f of lambda will go to 1, and thus the values of f tilde x and f tilde y remain unadjusted. For the second case, assume that the geometric sum of the unadjusted tire forces surpasses 1/2 times the friction limit, and this surpassing is indicated by this variable x here. Then, by this formula, lambda starts to assume values less than 1, and hence also f of lambda will become less than 1, and so the unadjusted longitudinal and lateral tire forces will be scaled by a factor between 0 and 1. Of course, the scaling is arranged in such a way that the geometric sum of fx and fy will never exceed the friction limit of mu fz.